In the earliest human eras, the solar system is not a concept that exists. The sky is not a place to travel through. It is a surface above the world filled with lights that move in patterns and return again. For small communities living close to seasons, rivers, and migrating animals, the heavens are a practical calendar and a source of orientation. The sun marks day and warmth. The moon marks the changing month. The stars mark direction and the turning of the year. These motions feel regular, but the space behind them is not yet imagined as a depth that can be crossed. The world is experienced as a bounded place with a ceiling, not as a planet in an open void. This earliest sky is read through immediate needs. A hunter or herder learns when rains return, when grasses rise, when ice retreats, when certain fish run upstream. The sky's cycles become signals for these changes. In many regions, the rising of particular star groups before dawn occurs around the same time each year. Over generations, these correlations become reliable guides. A bright star's first appearance at a certain season can mean planting time, sailing time, or a moment to move livestock. The meaning is practical even when it is carried through stories and rituals. The sky is above, not outward. In such a worldview, leaving the sky is not an idea because the sky is not a region. It is a boundary between the human world and whatever lies beyond human control. Many early cosmologies describe the heavens as a solid dome, a layered roof, or a set of levels stacked above the earth. The shape differs by place and tradition, but the common thread is closure. The sky contains the lights. It holds back waters, spirits, or a higher realm. The world below is where people live and die, where food is gathered, where fires burn. Movement is horizontal across land and sea. Vertical movement is rare and dangerous, associated with mountains, storms, and birds. The idea of crossing upward into the sky as a journey has no physical basis. Even the strongest imagination remains anchored to the body's limits. Yet within this closed sky, a first quiet step toward a deeper idea is already forming the realization that the lights move with rules. The moon cycle is counted. Eclipses are noticed. The sun's path shifts through the year, and its rise and setting points change along the horizon. Shadows shorten and lengthen. Over long time, careful observers begin to separate the sky from pure unpredictability. The heavens become orderly. Order invites measurement, and measurement invites the notion that the sky can be described rather than only narrated. This does not produce the thought of leaving, but it creates the mental habit that will later make such a thought possible. Another early step is the development of long-distance navigation. When people cross deserts, open seas, or wide plains, the sky becomes a map. A star's position at night provides direction. Constellations become stable reference points. Navigators learn that the sky's appearance changes with latitude, that certain stars rise higher or lower depending on how far north or south one travels. This experience hints that the observer's position matters. The sky is not a painted ceiling that looks the same everywhere. It responds to movement on Earth. The Earth is still not imagined as a globe by most, but the link between location and sky begins to feel real. The heavens become something that can be related to geometry, even if the geometry is still unspoken. Across different early societies, a special role is often given to the wandering lights, the planets, though they are not yet understood as worlds. They move against the background stars in ways that are slow and sometimes strange. They sometimes reverse direction relative to the stars, a motion later called retrograde. To an early watcher, this behavior distinguishes them from the fixed star patterns. The attention given to these wanderers is one of the first signs that the sky is not a single surface. If some lights behave differently, then the sky may contain layers or tracks. Even when these are explained through mythic beings or divine signs, the raw observational fact remains: not all lights share the same motion. Imagination in these eras often reaches upward in symbolic ways. There are stories of sky ladders, sacred trees reaching into the heavens, spirits traveling to the stars, heroes lifted by birds or storms. These are not travel plans. They are expressions of boundary crossing in a world where boundaries are felt in daily life. The boundary between life and death, the boundary between land and sea, the boundary between day and night, the boundary between the known and the unknown. The sky becomes a stage for the most distant boundary, the one that cannot be crossed by ordinary means. The presence of such stories is important because it shows that humans already practice a kind of mental departure. The mind can imagine a beyond even when the body cannot. But this beyond is not yet space. It is a realm, not a distance. The first age of imagining leaving what later becomes known as the solar system does not begin with rockets or with mathematics. It begins with a change in what the sky is allowed to be. For leaving to be imagined, the sky must become a place rather than a ceiling. The lights must become objects rather than signs. The distance between them must become a real depth rather than a symbolic separation. None of these shifts are immediate. They take centuries, often appearing first as small cracks in older pictures. A priest astronomer records a cycle with unusual precision. A sailor notices a pattern that holds across voyages. A builder aligns stones with solstices and sees that the sun's path is not arbitrary. A scribe compares observations made years apart and senses a consistency that belongs to nature rather than to story alone. Even as measurement grows, it remains tied to Earth. The earliest geometry of the sky is still geometry of angles and directions, not geometry of distance. A star's position can be described, but how far it is remains unknowable. The moon's size appears similar to the sun's size in the sky, yet they behave differently. The moon changes shape, revealing that it is not a simple light. The sun stays bright and constant, and its heat is felt. The planets vary in brightness and sometimes show phases, though such details require careful watching. Each of these observations contains a seed that will later grow into an object-based sky. Yet in the earliest age, the seed remains embedded in a world that is mostly local. In this local world, leaving the solar system cannot be conceived because there is no defined solar system to leave. There is only Earth-sky and the repeating motions that govern time. The boundary that matters is the horizon and the edge of known land. When people do travel far, they do so by moving across Earth's surface, gradually extending maps and trade networks. This kind of travel, slow and risky, shapes the imagination of distance. It teaches that the unknown can become known through persistence. It also teaches that distance has cost. These lessons will later be applied upward once the sky is reinterpreted as a space with places and paths. This first section holds the outermost world view because it is the widest layer of the topic. The age when humans first imagine leaving the solar system cannot begin until humans have a concept of a system around the sun and a sense of the sky as open depth. At the start, that framework is absent. What exists instead is a sky that is intimate, patterned, and bounded, serving life's rhythms rather than inviting departure. The next step inward is the recognition of wandering lights as distinct and trackable, because that recognition begins the slow separation between a single dome and a structured heavens, preparing the way for later models that place Earth among moving bodies rather than beneath a fixed roof. As careful watching continues across generations, the sky begins to sort itself into different kinds of motion. Most stars keep their patterns. They rise and set together with the daily rotation of the heavens and shift slowly through the seasons. Against them, a small set of lights behaves differently. These are the wanderers, later called planets. They do not keep a fixed position relative to the star patterns. They drift along a band of sky that later becomes known as the zodiac. Their motion is slow enough that it becomes visible only when compared across nights and weeks. Their behavior is not random, yet it is not as simple as the daily rising and setting. This difference is one of the first cracks in the early idea of a single uniform sky. The recognition of these wanderers is ancient, and it appears independently in many cultures. The visible planets are bright enough to be noticed without instruments. Their paths can be traced by anyone patient enough to watch and record. Over time, observers learn their rhythms. One bright object lingers near the sun and appears as a morning or evening star. Another moves more slowly and glows with a steady light. Others brighten and fade, sometimes becoming strikingly bright. The wanderers sometimes reverse their direction against the star background, moving backward for a time, before resuming their forward drift. This retrograde motion is especially important because it refuses to fit the simplest picture of lights glued to a single rotating dome. Early explanations often use layered heavens. If the sky is imagined as a set of shells or tracks, then wanderers can be placed on their own layers, each moving with its own pace. This is not yet a concept of physical space. It is a concept of organized motion. Yet organization makes room for more complex structure. The sky can be pictured as a machine of cycles rather than a single surface. When a mind can hold multiple layers, it can later hold depth. When it can hold rules, it can later hold causes. The practical work behind these ideas is observation. In some early societies, observers create long records of planetary positions, often tied to calendars used for agriculture and for civic planning. The records may not be purely scientific in modern terms, because they are often mixed with omens and interpretations. Yet the positional data itself accumulates. Over centuries, such records become powerful. They reveal that planetary motions repeat in long cycles, and that patterns that look irregular on short timescales can be predicted when seen across longer spans. Predictability is a quiet revolution. It suggests that the heavens operate according to stable principles. The need to predict eclipses plays a similar role. A solar eclipse is rare in any given place, dramatic when it occurs, and difficult to understand without a model. Lunar eclipses occur more often and are easier to observe across wide regions. Over time, observers note that eclipses occur in patterns tied to the moon's orbit and the alignment of sun, earth, and moon. Even if early explanations remain symbolic, the ability to anticipate eclipses strengthens the idea that the sky is governed by regularity rather than by whim. Regularity does not automatically create the idea of travel, but it begins to transform the sky from a realm of signs to a realm of mechanisms. As wanderers are tracked, they become entities that can be discussed as objects with behavior. This matters for imagination because an object can be moved in thought. A sign cannot. A sign points to meaning, but it does not belong to a physical story. An object belongs to a physical story even when the story is still incomplete. When planets are treated as objects with paths, the mind begins to treat the heavens as a place where motion happens in a structured way. This is the foundation for later models that treat planets as worlds, and for the later idea that worlds might be reached. Yet in this age, planets are still not worlds in the modern sense. They are usually considered lights, sometimes deities or embodiments of deities, sometimes omens, sometimes rulers of time. Their motion is tracked because it seems connected to terrestrial events. The separation between positional astronomy and interpretive astrology is not yet clear. Still, the act of tracking produces a discipline, careful measurement, repeated comparison, attention to small changes, and respect for long-term records. This discipline is one of the hidden roots of later scientific thinking. The band of sky where the wanderers move becomes an important concept. Observers notice that the sun's path through the year follows a line among the stars. The moon's path stays close to this line, but with its own tilt. The planets also stay near this band. This suggests a shared plane of motion. In modern terms, it reflects the plane of the solar system, but early observers do not need that interpretation to notice the fact. The existence of a shared band implies structure. Structure invites geometry. Geometry over time invites the possibility that the sky has depth and that the motions reflect the arrangement of bodies rather than the turning of a dome. Retrograde motion remains a central puzzle, a simple geocentric picture in which everything circles Earth in perfect circles struggles to explain why a planet sometimes moves backward relative to the stars. Early models introduce loops, epicycles, and combinations of circles upon circles. These models are complex, but they are also a form of progress. They attempt to preserve a rule-based sky by adding mechanism rather than surrendering to mystery. They also cultivate a habit of building models that can be checked against observations. A model that predicts where a planet will be next season is more useful than a story that cannot be tested. The growth of such modeling is part of the long path toward imagining departure, because it eventually makes the heavens feel like a knowable system rather than an unreachable ceiling. The wanderers also show that not all objects in the sky are equally distant in a conceptual sense, even if physical distances are not yet measured. The moon changes shape through phases. It also moves quickly across the sky and changes its position against the stars night by night. This suggests closeness compared with the fixed stars. Some planets show changes in brightness and in apparent size, implying that they move closer and farther. The sun and moon have apparent sizes that can be compared. These clues begin to create a ladder of near and far within the heavens. The latter is still qualitative, but it is a step toward a layered universe where some objects are nearer than others. Once nearer and farther are accepted, the idea of traveling outward becomes easier to form later because distance becomes part of the picture. This age also includes the first careful instruments, though simple by modern standards. Sightlines, gnomons, water clocks, and later armillary spheres are used to track positions and time. The point is not the sophistication of the device. The point is that the sky is being turned into data. The data is being compared across years. The sky is being treated as something that can be mapped. Still, the solar system is not yet imagined. The Earth is still the central ground of experience, and the heavens remain a realm of motion above it. The wanderers are recognized and tracked, and their patterns are incorporated into calendars and beliefs. This is a necessary stage. It creates a structured sky in which different bodies have different motions. It makes the sky thinkable in terms of mechanisms. It does not yet make leaving thinkable, because leaving requires a further shift. The idea that Earth itself is not the fixed center, and that the same physical rules apply to Earth and to the sky. The next inward step is the growth of measurement and scale, where observers begin to estimate sizes and distances in geometric terms, turning the heavens into something that has not only patterns, but measurable dimensions. Once the sky is treated as a set of motions that can be tracked, the next change is the slow arrival of scale. Patterns alone can describe where a planet will be. Scale asks how big the system is and how far its parts lie from one another. Early astronomy is mostly an astronomy of angles, because angles can be measured from a fixed point on Earth. Yet even angle measurement, when combined with geometry, can begin to imply distance. The moment humans begin to estimate the size of Earth, the distance to the Moon, and the relative spacing of celestial bodies, the sky begins to acquire depth. Depth is the first condition needed for any serious thought of departure, because leaving requires a place to go, not merely a pattern to observe. The earliest geometric approaches treat the Earth as a shape that can be measured. When thinkers and surveyors compare the angles of the sun at different latitudes, or compare the length of shadows at different locations, they can infer the curvature of Earth and estimate its size. This step matters because it detaches Earth from being a flat stage and makes it an object with a measurable form. Once Earth is a measurable object, it can be placed within a larger geometry. The heavens are no longer only above. They are around. With a measure of Earth's size, the Moon becomes a target for distance estimation. Lunar eclipses provide an opportunity because the Earth's shadow falls on the Moon and can be compared to the Moon's own apparent size. By observing the curvature and size of the shadow during eclipses, thinkers can infer relationships between Earth's size and the Moon's distance. Even if the exact numbers vary by method and by assumption, the concept becomes clear: the Moon is not just a light. It is a body at a calculable distance. This is a profound shift. A calculable distance turns the Moon into a place in space rather than a decoration on a dome. It also provides the first real yardstick beyond Earth. The Sun's distance is far harder to estimate, but attempts are made. By using geometry during certain alignments, and by comparing the apparent sizes and motions of the Sun and Moon, thinkers propose values for the Sun's distance. Early estimates often miss by large margins, but the act of estimating is itself transformative. The sun becomes an object at a distance, not an unreachable lamp. The sky becomes a geometry that can in principle be solved. When geometry enters the heavens become something that can be reasoned about without relying only on tradition. The planets also begin to acquire a kind of scale, though often in the form of relative distances rather than absolute ones. In geocentric models, the planets are arranged in nested spheres. The order is known through their observed motions and brightness changes. The Moon is placed closest, then Mercury and Venus, then the Sun, then Mars, Jupiter, and Saturn, and then the fixed stars. This ordering, while not the modern picture, already implies a layered system. The concept of nested spheres is both a constraint and a stepping stone. It keeps the universe closed, but it also introduces the idea that there is a structured space between layers. Once space between layers is acknowledged, a mind can begin to ask what fills it, how wide it is, and whether it could be crossed. In this period, the tools of measurement also develop. Angular measurement improves through devices that align sightlines with marked scales. Star catalogs grow. Observers notice small deviations and refine models. The emphasis is still on describing motion, but the precision of description makes geometry more effective. Better angles mean better distance estimates when geometry is applied. Even when distance remains uncertain, the concept that it is a solvable quantity grows stronger. Yet the deepest obstacle to imagining departure remains the physical impossibility of escaping Earth by any known means. In daily life, gravity is not described as a force, but its effects are obvious. Everything falls. Nothing rises without a push and then falls back. The idea of traveling to the Moon or to a planet remains beyond practical thought. Even when philosophers imagine travel, it is often imagined through supernatural means or through speculative mechanisms that do not connect to real engineering. The sky is becoming measurable, but the body remains grounded. This is why the first age of serious imagination about leaving the solar system cannot occur until the physical relationship between Earth and the heavens is reinterpreted. Still scale changes imagination slowly. When Earth is measured, it becomes clear that even traveling around Earth is a major undertaking. Distance becomes a known cost. If Earth is a sphere thousands of kilometers across, then its surface journeys are long, and its size makes it plausible that the heavens are larger still. The mind that accepts large distance on Earth can more easily accept vast distance in space. It also begins to accept that there may be no quick way to cross such distance. This encourages a form of imagination that is less about sudden leaps and more about gradual motion. That is closer to how real space travel will later work. The measurement of the star sky also begins to imply an even greater scale. As observers compare the positions of stars across years, they can search for parallax, the tiny shift in a star's position due to Earth's movement. Early instruments do not detect it for stars, which suggests that the stars are extremely far away. This absence of detectable parallax strengthens the idea that the fixed stars are not attached to a nearby shell, but lie at immense distances. Even without a number, the implication is enormous. The universe becomes deep. If the stars are far beyond the planets, then the planetary region becomes a smaller interior part of a much larger space. This is a quiet way the solar system begins to emerge as a distinct region. The planets are near compared with the stars. At the same time, the apparent motions of planets are still explained through complex geometrical constructions in geocentric frameworks. These frameworks can predict positions fairly well, and they satisfy the desire for a regular cosmos. Yet their complexity also keeps the heavens as a system of abstract circles rather than a system of physical bodies moving through open space. The space between spheres is not always treated as empty space. It is often treated as an ether or as a set of crystalline shells. Such pictures can discourage the idea of travel because a solid shell cannot be crossed like open space. The sky remains a structure to be contemplated rather than a realm to be entered. The growth of scale therefore produces a tension. On one side, geometry and measurement turn the moon and sun into bodies at distances and the stars into extremely remote lights. On the other side, cosmological models still often treat space as layered and closed with physical barriers. The mind is approaching the idea of an open, traversable system, but it has not yet arrived. The age of first imagining leaving the solar system requires the dissolution of the closed shell idea and the acceptance that space is continuous and that Earth itself is a moving body in that space. This section holds the measuring impulse as the key change. Once distances are estimated and Earth is measured, the heavens gain depth and size. The next step inward is the formation of structured celestial models that place Earth among spheres while still enclosing it. Because these models make the system explicit, they define a cosmic architecture. From there, a later shift will move the center away from Earth and open the architecture into an infinite or at least unbounded space, creating the conditions where leaving can be imagined not as myth, but as an extension of motion through a continuous realm. As measurement and modeling mature, the heavens are increasingly pictured as a structured architecture. In many classical traditions, the cosmos becomes a system of nested spheres centered on Earth. Each sphere carries a body, first the moon, then Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and beyond them, the sphere of fixed stars. The arrangement differs by school and era, but the overall form remains a layered universe. This model does something important for the later idea of leaving. It turns the sky into a system with parts and order. It makes an implicit claim that the heavens are organized and knowable. Yet it also keeps the universe closed like a set of shells, and closure makes departure difficult to imagine as a real journey. The nested sphere model is therefore both a bridge and a barrier. In this architecture, the Earth is the unmoving center. The daily rotation of the heavens is usually explained as the turning of the outer sphere. The planets move on their own spheres, often with additional small circles, to account for observed irregularities. This layered picture is attractive because it preserves the sense of a stable center and because it matches human experience. The ground does not feel like it moves. The sky appears to rotate. The model also aligns with certain philosophical views of order where the heavens are perfect and the earth below is changeable and imperfect. The sky's motions can be described with geometry, and the nested spheres provide a framework for prediction. The framework encourages careful reasoning about relative distances. If one sphere lies beyond another, then the object it carries must be farther. The order of spheres sets a relative map of the planetary system. even if absolute distances remain uncertain. In many versions, the fixed stars are placed at an enormous distance so far that they show no measurable parallax. This makes the planetary spheres a small inner region in comparison. In a quiet way, a concept resembling the solar system begins to appear as the inner set of planetary motions distinct from the distant star sphere. Even though the system is not yet sun-centered, it is still a system of multiple bodies with ordered relations. At the same time, the nested sphere picture tends to treat the space between spheres as filled with a medium. Some versions imagine the spheres as solid, crystalline, or otherwise structured. Others imagine a refined substance that carries motion. In either case, the region between Earth and the stars is not yet the empty vacuum of modern space. It is a connected fabric of shells or layers. This matters because travel through such a cosmos is not straightforward. A ship can sail through water because water yields. A solid sphere does not. Even a fluid medium in the heavens is not yet conceived as something that can be traversed by technology. The sky remains a realm whose structure explains motion, not a realm designed for passage. Within this world, picture imagination about leaving takes forms that are still symbolic or philosophical rather than technical. Some thinkers imagine the soul ascending through spheres. Some imagine the gods inhabiting these layers. Some imagine the stars as fires set in the outer sphere. These are movements in thought, not in mechanism. Yet the very existence of multiple layers invites the idea that there is a sequence of regions above each with its own character. This regionalization of the heavens is a necessary condition for later travel thinking. Before one can imagine leaving a system, one must imagine a system with layers. The nested sphere model also strengthens the use of mathematics as a descriptive tool. Planetary positions can be predicted using combinations of circles. The predictions can be compared with observations. If the predictions fail, the circles can be adjusted. This is not the same as modern physical science, but it is a form of model-based reasoning. It creates a culture where it is normal to represent the sky in a structured, quantitative way. Over time, this culture supports the idea that the heavens are not beyond analysis. They can be represented, improved, and understood. That habit is a prerequisite for later imagining of travel, because travel requires treating the heavens as a space with rules rather than a realm of pure mystery. Yet the nested sphere cosmos also imposes a strong psychological boundary. If the fixed stars are on a sphere that encloses everything, then the cosmos has an edge. Beyond that edge lies nothing or a different realm. The universe is finite and complete. A finite cosmos can still, in principle, be crossed. But in this model, the spheres are perfect, and the earth is the center, and the boundary between earth and heaven is not a place for human bodies. The air above earth thins and ends, and beyond it is ether or a divine region. Humans are not imagined as equipped to survive there. The conditions of life are assumed to belong only to Earth's lower region. This assumption discourages the idea of leaving as an achievable project. The moon becomes the nearest object that could, in theory, be reached. In some stories and thought experiments, people imagine the moon as a place. Yet even then, the journey is often framed as impossible for ordinary bodies. The imagined traveler might ride a giant bird, be carried by winds, or experience a miraculous ascent. These narratives reveal a desire to connect Earth to the heavens, but they also reveal the absence of a mechanism that could make such a connection plausible. Without a mechanism, the idea remains a fantasy rather than a plan. As long as the cosmos is layered in solid or semi-solid spheres, the idea of leaving the solar system cannot form in a modern sense. Leaving requires a concept of open space beyond the planetary region. It requires a recognition that the planets are objects moving through that open space rather than lights carried on shells. It also requires a sense that Earth is not the fixed center, because a fixed center implies that the system's natural frame is Earth-bound. A moving Earth, by contrast, makes motion through space feel like a shared condition of all bodies. Still, the nested sphere model contributes an important psychological shift. It normalizes the idea that the heavens are a structured arrangement, not a flat decoration. It gives a place for each body and a set of relations among them. It encourages the mind to think of a cosmic map. A map is not yet a path, but it is closer to a path than a mythic sky. When the time comes for the map to be redrawn with the sun at the center and with space treated as continuous, the map-making impulse will already exist. Another quiet contribution of this era is the gradual awareness that models are tools. Different models can describe the same observations. This awareness begins to separate the question of what is seen from the question of what is true. A model can be judged by predictive power. When a model becomes a tool rather than a final truth, it becomes easier to replace it with a different model that better fits evidence. This flexibility will matter when heliocentrism appears and challenges the Earth-centered structure. This section holds the sphere architecture as a necessary stage. It makes the heavens into a system, but keeps it closed. The next inward step is the shift to the sun-centered idea, because that shift breaks the intuitive centrality of Earth and recasts the planets as bodies in motion around a shared center. Once the sun becomes the organizer, the inner planetary system begins to resemble what later becomes known as the solar system, and the idea of leaving it can begin to take a different, more physical form. The shift toward a sun-centered picture is not simply a change of viewpoint. It is a change in what the heavens are allowed to be. When Earth is placed in motion around the sun, the sky is no longer a set of shells turning around a fixed center. It becomes a system of bodies sharing a common space, each moving according to a rule. This shift is slow and contested, but it is one of the key moments on the long path toward imagining departure beyond the solar system. Before a person can imagine leaving the solar system, there must be a solar system to imagine a coherent set of bodies around a central star. Heliocentrism provides that coherence. A sun-centered model offers a simple explanation for several puzzles that burden geocentric models. Retrograde motion becomes a matter of perspective. When Earth overtakes an outer planet in its orbit, the planet appears to move backward against the stars for a time. The planet is not reversing its true motion. The apparent reversal is a result of two moving observers, like two boats passing on a river. This explanation transforms retrograde motion from an intrinsic oddity to a natural outcome of relative motion. The heavens become less like a set of special exceptions and more like a space where the same kind of motion applies to multiple bodies. In a heliocentric picture, the ordering of planets gains a new meaning. Their periods and distances align in a coherent pattern. Inner planets orbit faster, outer planets orbit slower. The Sun becomes the central source of order. Earth becomes one planet among others. This does not yet imply that Earth is physically similar to the other planets, but it begins to remove Earth from its special fixed role. The mental distance between Earth and the rest of the cosmos narrows. That narrowing is essential for later travel imagination. If Earth is one moving body in space, then movement through space is not alien. It is already happening. Heliocentrism also supports the growing use of mathematics for describing the system. Once the Sun is treated as a central reference, orbital periods can be compared systematically. Relative distances can be derived from the geometry of orbits. Even before absolute distances are firmly established, the solar system becomes a proportional structure. The planets occupy a hierarchy of spacing. The system has an interior and an exterior. It becomes possible to speak of regions, inner planets, outer planets, and beyond. This regional language is one of the first steps toward the later phrase leaving the solar system, because it implies that the system has an extent, and that beyond it there is something else. Yet early heliocentric models still often rely on circular motion and retain some epicycles to match observed positions. The shift is therefore not an immediate simplification in all details. It is a change in the organizing center. That alone is enough to change imagination, because it makes the Sun a kind of anchor, and it makes Earth's motion part of a larger pattern. The old picture of a sky turning above a still Earth begins to weaken. The Sun-centered idea also interacts with the development of instruments. As telescopes improve, observations challenge older assumptions. The phases of Venus are a crucial example. Venus shows a full set of phases from thin crescent to near full, consistent with a heliocentric arrangement, where Venus orbits the Sun inside Earth's orbit. In a strict geocentric model where Venus always lies between Earth and the Sun, such phases would not appear in the same way. Observations of Jupiter's moons also matter, because they show smaller bodies orbiting a planet, offering a miniature example of a system within a system. If moons can orbit Jupiter, then not everything in the heavens orbits Earth. The idea that Earth must be the universal center loses force. This loosening opens space for the solar system as a real structure, rather than a philosophical arrangement. As the solar system takes shape as a set of orbits around the Sun, the stars also shift in meaning. In the older sphere model, the fixed stars are attached to a shell that encloses the planetary system. In the newer picture, the stars begin to look less like a boundary and more like distant objects. The lack of observed parallax had been used to argue for a fixed Earth. In a heliocentric model, the same lack of parallax can be taken to imply that the stars are extremely far away. This enlarges the universe dramatically. If the stars are distant, then the solar system becomes a small island within a vast space. An island suggests the possibility of seas between islands. This is a quiet way the mind begins to separate the solar system from the rest of the cosmos. The acceptance of heliocentrism does not immediately produce an age of imagining spacecraft. The practical means of leaving Earth remain absent. Air is still the medium of flight, and above it, the conditions are unknown. Yet the conceptual basis for leaving begins to change. Once Earth is a planet, the Moon becomes a neighbor world rather than a lamp. Once planets are worlds in motion, the thought of moving from one to another becomes less like crossing into a divine realm and more like traveling to another place. The distance remains enormous, but the category changes. It becomes a physical problem rather than a spiritual boundary. This shift also changes the meaning of the sun. In many earlier pictures, the sun is a light carried by a sphere, sometimes a divine object, sometimes a ruler of time. In the heliocentric picture, the sun becomes the central body around which the planets move. It becomes the source of illumination and heat for the whole system. It becomes the center of the map. When the sun becomes the map's center, the system becomes something that can be imagined from outside as a whole. This outside view is a step toward imagining leaving, because leaving requires the ability to picture being somewhere other than Earth, while still understanding the system's layout. Heliocentrism also encourages a new kind of question. If Earth is moving through space, what holds people to it? Why do people not fall off? Why do birds and clouds and oceans remain attached? These questions lead toward the concept of gravity as a universal influence. Without gravity, a moving Earth would be difficult to accept. As gravity becomes more defined, the idea of escape becomes thinkable in principle. Escape is not yet a practical goal, but it becomes a meaningful concept. There is a force that holds bodies, and in principle, a body could overcome it. The imagination begins to shift from magical ascent to conditional motion governed by laws. In this age, the first serious thought experiments about traveling beyond Earth begin to appear in a new tone. They are not only myths, they are sometimes framed as speculative extensions of natural philosophy. Writers might imagine the conditions on the Moon or other worlds, discussing air light and landscape. These discussions can still contain fantasy, but they are grounded in the new idea that other worlds are physical places. This is the beginning of an imaginative realism that will later grow into more technical visions. The age when humans first imagine leaving the solar system cannot fully arrive here, because leaving the solar system requires more than imagining Earth as a planet. It requires imagining the solar system as one system among many, and it requires imagining motion through a vast, possibly infinite space. The sun-centered idea is a major inward step because it builds the system and removes Earth from the center. The next inward step is the emergence of infinite or at least unbounded space in early modern thought. Because once the cosmos is no longer enclosed by a star sphere, the idea of going beyond the solar system becomes conceptually possible. Without an enclosing shell, there is no final roof to stop imagination. There is only space extending outward, inviting questions about what lies beyond the sun's region and whether anything could travel there. Once the sun-centered picture begins to take hold, another transformation follows that is quieter but equally profound. The cosmos begins to lose its enclosing walls. The old image of a finite set of nested spheres capped by a star shell becomes harder to maintain in the face of new observations and new arguments. Space begins to be imagined as extending indefinitely, or at least without a known edge. This change is essential for the later idea of leaving the solar system. If the universe is a closed structure with a fixed outer sphere, then there is little conceptual room for journeys beyond the planetary region. If the universe is open and unbounded, then the solar system can be thought of as a local neighborhood within a larger expanse. A local neighborhood can be left. The first steps toward an open cosmos are often philosophical and mathematical rather than mechanical. Thinkers ask what it would mean for the universe to have an edge. If there is an edge, what lies beyond it? If one could reach it, could one extend a hand beyond? These questions are not asked to design a journey. They are asked to test the coherence of an enclosed universe. In doing so, they make the idea of an edge feel less stable. The universe begins to be pictured as space itself, not as a container. Observations support this change by undermining the idea of a perfect, unchanging celestial realm. Telescopes reveal features on the moon showing mountains and shadows. They reveal spots on the sun showing change. They reveal the phases of Venus supporting heliocentrism. They reveal moons around Jupiter showing that centers of motion can exist elsewhere. These observations do not by themselves prove an infinite universe, but they weaken the sharp division between a perfect heaven and an imperfect earth. If the moon has mountains, then the moon resembles Earth in some ways. If the sun has spots, then even the sun changes. The heavens begin to feel like a physical realm with variety and imperfection, rather than a set of flawless shells. A physical realm is easier to imagine as continuous space. The idea that stars are distant suns contributes to the sense of openness. If stars are like the sun, then they are not decorations on a shell. They are bodies distributed through space. If they are distributed through space, then the space around them must be real and extended. The stars begin to be imagined not as a boundary, but as inhabitants of a vast domain. Even without precise distances, the sheer number of stars visible and the lack of measurable parallax suggest great depth. Depth invites the idea that there may be more stars beyond the ones visible, and more space beyond those stars. The sky becomes less like a ceiling and more like a view into a deep environment. An open cosmos also changes the meaning of the solar system itself. In a closed sphere model, the planetary system is essentially the cosmos. The planets and stars are part of one structured shell arrangement. In an open model, the planetary system becomes one system among many possible systems. The sun's region becomes local. The stars become other centers. The mind begins to imagine that the sun's influence might be limited, and that beyond it, there is a different realm where other stars dominate. This is the first conceptual form of leaving the solar system, not a journey yet, but a recognition that there is an outside. Yet even as space becomes open in thought, the means of movement remain tied to air and to earthbound technology. Flight is limited to birds and to imagination. The notion of traveling beyond the atmosphere has no practical foundation. This gap between conceptual openness and practical impossibility is important. It means that early imaginings of leaving remain literary and philosophical. They explore the idea of space as a medium, the idea of other worlds as places, and the idea of a vast universe that could in principle be traversed, even if the method is unknown. This is a new kind of imagination, not mythic ascent through divine layers, but a thought of travel through continuous space. In this era, Writers begin to imagine voyages to the moon and beyond in forms that blend satire, speculation, and emerging natural philosophy. These works are not engineering documents. They often use fantastical methods of travel. Yet their importance lies in how they treat the destination. The moon is described as a world with terrain, sometimes with inhabitants, sometimes with strange conditions. The traveler is not entering a spiritual realm. The traveler is crossing a distance. This framing is a key step toward the later age when leaving the solar system is imagined as a technical challenge. It also shows that the imagination of departure grows first, where constraints are loosened in writing and thought experiments, before it is constrained again by physics and engineering. The growing sense of an open universe also encourages the idea that motion is not confined to the planetary band. If space extends everywhere, then there is no special track that holds the planets like beads on a wire. The planets follow paths because of their relation to the sun, not because they are embedded in a physical shell. This opens a conceptual route for travel. A craft could in principle follow its own path through space, not limited to the celestial machinery of nested spheres. The path could be chosen. It could be shaped. This is a necessary condition for imagining leaving the solar system, because leaving requires departing the plane and region of the planets and entering a wider space. This period also sees the early development of a more physical notion of vacuum. Philosophers and experimenters debate whether a true vacuum can exist. Experiments with pumps and sealed containers begin to show that air can be removed, and that in the absence of air, sound does not travel and flames do not burn. These experiments are small, but they matter. They begin to reveal that the space above the atmosphere may be a place without air. If space has no air, then human life cannot persist there without protection. This introduces a new kind of constraint, not a mythical barrier, but an environmental one. The imagination of travel becomes more realistic because it begins to include the idea that conditions change with altitude and that survival requires technology. The open universe also changes the emotional texture of the sky. It can create a sense of vastness and remoteness that is different from the earlier enclosed dome. Yet within the calm tone of this narrative, the key point is structural. An unbounded space allows the solar system to be a region rather than the whole. It allows a question to form: where does the sun's region end? What lies beyond? How could anything cross that boundary? These questions are the early shape of imagining leaving the solar system. They are no longer questions about passing through a divine shell. They are questions about traveling through space to another region governed by other stars. Still, the idea remains mostly abstract until the laws of motion are unified. Heliocentrism places Earth among the planets. An open cosmos places the solar system within a larger space. The next inward step is the development of physics that applies the same rules to falling stones and orbiting moons. When the same law governs both, then leaving becomes thinkable as a matter of speed and force, rather than as an act of crossing into a different realm. That unification comes with the emergence of universal mechanics, where gravity and motion are treated as universal phenomena. Once that happens, the imagination of leaving can begin to attach to numbers, and numbers can begin to suggest that leaving is possible in principle, even if not yet in practice. When the same laws of motion begin to be applied to Earth and to the heavens, the idea of space travel changes in character. The earlier open cosmos provides room for departure, but it does not provide a method. Universal mechanics provides a method in principle. It describes how bodies move under forces, how orbits form, and how motion can change. Once the orbit of a planet is treated as a natural consequence of motion and gravity rather than as a path imposed by a celestial shell, the solar system becomes a physical machine that can be understood and, in principle, navigated. This is a critical step toward the age when humans can imagine leaving the solar system not as a literary dream, but as a problem that might yield to calculation. The key shift is the unification of falling and orbiting. On Earth, objects fall toward the ground. In the sky, the moon does not fall to Earth in the ordinary way. Universal mechanics reframes this. The moon is falling, but it is also moving sideways fast enough that it keeps missing Earth as it falls, tracing an orbit. In this view, an orbit is not a special heavenly motion. It is a natural outcome of a body moving under gravity with sufficient sideways speed. This idea is simple, but it is transformative. It suggests that a body launched with the right speed could also orbit Earth. It suggests that motion can be shaped by speed rather than by divine placement. It turns the heavens into a place where the same logic that governs a thrown stone governs a planet. Once gravity is treated as a force that acts at a distance, the solar system becomes a system held together by a central influence. The planets follow their paths because of the sun's gravity, and moons follow their paths because of their planet's gravity. This provides a physical explanation for the structure of the solar system. It also means that leaving a gravitational domain becomes a question of energy. A traveler would need to move fast enough to escape a body's pull. The idea of escape begins here as a physical concept. It is not yet expressed in the everyday phrase escape velocity, but the principle is present. There is a speed above which a body will not fall back. Universal mechanics also introduces a new way of imagining trajectories. A path through space can be plotted, at least in principle, by knowing initial speed and direction and the gravitational influences along the way. The solar system becomes navigable in thought. This is different from earlier imagination because it replaces magic with geometry and force. A ship could in principle be launched toward the moon. It could in principle be launched toward another planet. It could in principle leave the sun's domain if it had enough energy. The word enough becomes central. Travel becomes limited by capability rather than by category. The capability is still missing. In the era of universal mechanics, no human-built engine can accelerate a craft to the speeds required to reach orbit, let alone to leave Earth and then leave the solar system. But the conceptual barrier is lowered. Once a question can be expressed in terms of speed and force, it can be placed on a continuum. It is no longer impossible by definition. It is difficult by degree. This is the moment when leaving the solar system becomes imaginable in a new way, as an extension of the same physics that governs smaller motions. The discovery and mathematical description of the relationship between orbital period and distance also strengthens the sense of a system with scale. When the spacing of planets and their periods can be related through a rule, the solar system becomes quantifiable. Quantification changes imagination. A person can begin to picture how far Mars is relative to Earth, how long it takes to go around the Sun, and how much speed might be required to travel between orbits. Even if the numbers are rough, the structure becomes a map that can in principle be used for planning. Universal mechanics also clarifies the nature of comets. Comets are observed as unpredictable visitors with long tails. Over time, their paths are recognized as orbits often highly elongated, sometimes taking them far beyond the planets and then back again. This recognition matters because it shows that bodies can travel far outward from the Sun and return crossing the planetary region and the outer darkness. Comets become natural examples of leaving and returning within the solar system. They demonstrate that the solar system extends far beyond the planets, and that motion through those far regions is possible for natural bodies. This expands the mental map of the solar system's extent. It also suggests that a human-made object could in principle follow a similar long orbit if it could be launched with the right conditions. Yet universal mechanics also reveals a sobering detail: the energies involved are large. To place an object into orbit requires a substantial speed. To escape Earth requires more. To escape the Sun requires still more. The requirement grows with each step. This does not stop imagination, but it shapes it. It replaces vague longing with an awareness of cost. A journey to another planet is not like a voyage across an ocean. It is a voyage that demands a speed that no sailing ship can provide. The realization of this gap between required speed and available technology keeps leaving the solar system in the realm of thought for a long time. Even so, the presence of a clear gap can stimulate technological imagination. If a speed is required, then one can ask what kind of engine might produce it. If the air thins and ends, one can ask what kind of propulsion does not rely on pushing against air. These questions begin to turn speculative writing toward mechanical invention. They also begin to create a new kind of confidence, not that the journey will happen soon, but that the journey belongs to the same physical universe as everything else. The age of universal mechanics also changes the meaning of the word world. The moon becomes a body governed by gravity like Earth. Planets become bodies governed by the sun. The stars, increasingly understood as distant suns, become part of a larger gravitational environment. This does not yet produce the idea of interstellar travel in a serious sense, because the distances are still overwhelming. But it begins to place the solar system within a larger physical universe where other systems might exist, governed by the same laws. Once that is accepted, the idea of leaving the solar system becomes more than a poetic metaphor. It becomes a logical possibility in a universe with consistent rules. Another important shift is the growing distinction between what is imagined and what is physically possible. In earlier eras, imagination and possibility are not always separated because many natural processes are not understood. With universal mechanics, constraints become visible. A person can calculate what would be required. This creates a new form of imagination that is disciplined. It can imagine a journey and also recognize the difficulty. It can imagine leaving the solar system and also accept that the required speeds are far beyond current means. This disciplined imagination is the seed of later engineering visions. This section holds universal motion as the key inward change. It makes leaving a matter of speed and energy rather than a matter of breaking into a different realm. The next inward step is the emergence of explicit calculations of escape and the 19th century growth of popular and scientific imagination about space travel. In that era, the idea of leaving Earth, and even leaving the solar system, begins to be entertained more widely, not because the technology exists, but because the physical framework now supports it, and because industrial society begins to produce machines that make high-speed motion less abstract. Once universal mechanics provides a law-based picture of the heavens, the next stage is a broadening of the idea that motion is not only describable, but controllable. This stage unfolds over centuries as mathematics, engineering, and industry reshape daily life. The 19th century is a central period in this transition because it combines mature celestial mechanics with a society increasingly comfortable with machines' energy and long-distance travel. In this environment, the imagination of cosmic travel becomes more common and more detailed. It remains mostly speculative, but it shifts in tone. It begins to feel like a question of engineering and physiology rather than a question of myth. This is a step toward imagining leaving the solar system, because leaving the solar system requires first imagining leaving Earth reliably. In the 19th century, the solar system is increasingly understood as a physical system with measured distances. The astronomical unit becomes a meaningful scale through improved observations and methods. Planetary motions are predicted with high precision. Comet orbits are calculated and compared. The system feels mapped. It is not fully known, but it is structured. This mapping does not directly create the idea of leaving, but it creates a sense that the system has a shape that can be navigated. The more the system is mapped, the more the mind can picture it as a place one could move through. At the same time, industrial technology makes high speed less abstract. Steam engines and railways allow humans to travel faster than any animal on land. Steamships shorten ocean crossings. Telegraph lines send information faster than any messenger. These changes alter what people consider possible. They show that human-built machines can overcome old limits. They do not suggest that space travel is close, but they create a cultural habit of expecting that new machines can change the relationship between distance and time. When distance becomes conquerable on Earth, it becomes easier to imagine conquering distance beyond Earth. Scientific understanding of the atmosphere also changes. Ballooning demonstrates that humans can rise high above the ground and survive for a time, though with difficulty. Observers learn that air becomes thinner with altitude, that breathing becomes difficult, and that cold increases. These experiences provide a physical lesson. Leaving the surface changes the environment. Space begins to be imagined not as a realm of pure spirit, but as a region with conditions that can be hostile. This is important because it introduces the idea that technology could provide protection as clothing and shelters do on Earth. The concept of a pressurized cabin is not yet realized, but the need for protection becomes imaginable. In this period, the concept of escape becomes more explicit in scientific language. Celestial mechanics implies that a body can be launched with enough energy to leave Earth's gravitational hold. The mathematics of energy and velocity becomes a tool for describing what would be required. Even if the term escape velocity is not used widely in popular discourse, at first the idea is present: there is a threshold speed. This threshold is not a mystical barrier. It is a calculable number. Once the threshold is known, the question becomes whether any engine could produce it. The idea of leaving Earth becomes a quantitative challenge. Popular imagination responds. Fiction writers explore journeys to the moon and beyond, often using speculative propulsion. These stories vary in realism. Some use cannons, some use imagined fuels, some use other devices. Many details are incorrect by later standards, but the framing matters. Travel is treated as a technological act. The traveler is a human body in a vehicle facing acceleration, cold, airlessness, and distance. The story's logic begins to borrow from science even when it stretches it. This borrowing helps normalize the idea that a machine could carry a person beyond Earth. It also introduces the idea that space is a medium through which one travels, not a realm one enters by transformation. In parallel, scientific and engineering discussions begin to touch on rockets, though early rockets are mostly simple weapons and signals rather than vehicles. The principle of rocket propulsion is known: a rocket moves by expelling mass backward, and it does not require air to push against. This is a crucial point. If a rocket can work in a vacuum, then a propulsion method exists that is compatible with leaving the atmosphere. The challenge is not the principle. The challenge is performance. A rocket must have enough thrust to lift itself and enough efficiency to reach orbital speeds. In the 19th century, materials, fuels, and control systems are not yet able to do this. Yet the existence of the principle keeps the door open. It allows the imagination of leaving to attach to a real physical mechanism rather than to fantasy alone. The 19th century also refines the understanding of energy. Thermodynamics formalizes the relationship between heat work and efficiency. This matters for space travel imagination because it shapes expectations about engines. People learn that no engine can convert heat to work with perfect efficiency. They learn that energy must be carried and managed. These ideas make the challenge of space travel more grounded. They also make it clearer why leaving the solar system is a far more difficult project than crossing an ocean. The energy required to accelerate a vehicle to orbital speed is enormous compared with everyday travel. The energy required to accelerate a vehicle to escape the sun's gravity from Earth's orbit is larger still. The energy scale begins to be seen as a central limitation. In this period, astronomy also begins to reveal that the sun is not the only star with physical processes. Spectroscopy allows scientists to analyze the light of the sun and stars and infer the presence of chemical elements. The stars begin to feel like physical objects with material composition, not just distant lights. This supports the earlier idea that stars are suns. If stars are suns, then the solar system is one example of a broader category. This does not yet prove that planets exist around other stars, but it makes the concept plausible. The imagination of leaving the solar system gains a new possible destination category. Other star systems might exist with their own worlds. Leaving becomes not only a matter of reaching a boundary, but a matter of potentially traveling to another system. The distance remains enormous, but the concept becomes richer. At the same time, a more disciplined skepticism grows. As scientific education spreads, people become more aware of physical constraints. A cannon-fired projectile to the moon, for example, is recognized as potentially lethal due to acceleration. The need for air and pressure becomes clearer. The idea of infinite fuel or magical propulsion becomes less acceptable in serious discussion. This skepticism does not kill imagination. It shapes it. It pushes imagination toward problems of propulsion, life support, and navigation. This is a necessary stage for eventually imagining leaving the solar system in a serious way, because leaving requires confronting the long duration and the harsh environment. The 19th century, therefore, forms a bridge. It takes the law-based universe of universal mechanics and places it in a culture of machines and measured energy. It produces stories that popularize the idea of technological space travel. It produces early scientific discussions that identify rockets as a viable mechanism in principle. It deepens the physical understanding of the environment beyond Earth. Yet it does not yet deliver a practical method to leave Earth, which means it cannot yet deliver a practical method to leave the solar system. The imagination is still ahead of capability. The next inward step is the point where rockets move from principle to calculation, where individuals begin to treat space travel as an engineering project and derive the mathematics that links propellant vehicle mass and achievable speed. This is the stage where leaving Earth becomes physically plausible on paper, and where leaving the solar system begins to appear not as an unreachable dream, but as an extrapolation of calculated trajectories and calculated speeds. The moment the imagination of space travel begins to harden into a technical program is the moment rockets are treated not merely as devices, but as vehicles whose performance can be calculated. This shift occurs as mathematics, physics, and engineering converge on a simple truth. To travel beyond Earth's atmosphere, a machine must carry its own reaction mass and expel it at speed, and the relationship between carried mass and achieved speed is not linear, it is exponential. This insight does not instantly produce spacecraft, but it changes the character of the question. Leaving Earth becomes a matter of design, staging, and propellant choice. Leaving the solar system becomes an extension of the same calculation, pushed to larger energies and longer durations. The central tool is the rocket equation, which links the change in velocity a rocket can achieve to the exhaust speed of its propellant, and to the ratio between its initial mass and final mass. This relationship reveals that achieving high speed requires either very efficient exhaust, very large propellant fractions, or multiple stages that discard empty tanks and engines along the way. The rocket equation is unforgiving. It shows why a single-stage vehicle with low exhaust speed struggles to reach orbital speed. It also shows why leaving Earth and then leaving the Sun's gravitational hold requires careful architecture. Even if the detailed numbers are not in public view, at first the principle becomes a foundation. A dream becomes a spreadsheet of mass ratios, fuels, and achievable velocities. This period includes thinkers and engineers who begin to propose multi-stage rockets and to analyze how a rocket could reach orbit. They consider propellants, structural mass guidance, and stability. They also begin to consider life support in a technical sense, asking how a crew could survive in a sealed environment, how air could be refreshed, and how heat could be managed. These considerations remain speculative, but are now grounded in engineering logic. A vehicle is no longer an imagined capsule carried by fantasy. It is a machine that must obey known laws and carry known systems. The idea of leaving the solar system in this context begins as a quiet extension of orbital mechanics. Once a rocket can place a payload in orbit, it can also in principle increase that payload's speed to escape Earth. Once it can escape Earth, it can also in principle adjust its trajectory around the Sun. A body that escapes Earth still orbits the Sun. To leave the solar system in a strict gravitational sense would require a trajectory that is unbound from the Sun. That requires additional speed. This is not yet framed as leaving the solar system in popular terms, but the physics implies it. There is an energy threshold for solar escape, just as there is for Earth escape. The universe of mechanics makes no special exception for the Sun. Early technical discussions of interplanetary travel tend to focus first on the Moon and on nearby planets, because they are within a scale that can be imagined as reachable by incremental progress. Yet even within these discussions, the idea of a craft leaving the planetary region can appear as a consequence of a high-energy trajectory. If a vehicle is sent toward an outer planet and receives a gravitational boost, it may end up on a path that does not return. Even if the mission's intent is not to leave, the physics of trajectories makes leaving a possible outcome. This is another kind of imagination. Leaving can happen as a byproduct of following the rules. As calculations become more sophisticated, engineers begin to consider not only propulsion but navigation. A spacecraft must know where it is and where it is going. It must correct its course. It must communicate. These requirements become more daunting as distance grows. Communication delays increase. Signals weaken. Guidance must be reliable. These constraints help clarify why leaving the solar system is not simply a matter of reaching a high speed once. It is a matter of sustaining a mission over years or decades. The rocket equation can tell how to reach a speed, but it does not guarantee that a vehicle can survive long enough to use that speed to cross the vast outer distances. Technical rocketry also becomes connected to institutional and military interests, because rockets have immediate applications as weapons and as delivery systems. This connection accelerates development, though not always in the direction of peaceful exploration. Yet it has an indirect effect on imagination. When rockets are built and tested, they become visible proof that propulsion without air is real. The concept of leaving Earth becomes less speculative. As capabilities grow, the old boundary between sky and space begins to weaken in public thought. The sky becomes a place that might be entered with a machine. In the early 20th century, the idea of space travel also becomes part of a broader modern imagination, shaped by rapid technological change. Airplanes become common. Radios connect continents. Electricity transforms cities. In this setting, the idea of a machine leaving Earth feels less like an ancient fantasy and more like a plausible future project. Yet this plausibility is still fragile because the energy required to reach orbit remains enormous and the control needed to guide a rocket remains challenging. Rockets that exist at this stage are often unstable, inefficient, and unreliable. The imagination is moving faster than the hardware, but it is now moving along a track defined by physics rather than by metaphor. The idea of leaving the solar system also begins to sharpen as the solar system itself becomes more clearly defined. The sun is recognized as a star. The planets are recognized as worlds. The space between them is recognized as vacuum. The outer region is recognized as extended with comets on long orbits. The solar system can therefore be pictured as a domain around the sun. Once it is pictured as a domain, it can be pictured as something that has an outside. This does not yet specify the heliosphere boundary, because plasma physics and the solar wind are not yet fully understood at this stage. But it does allow a general sense that the sun's influence weakens with distance and that beyond some far reach lie other stars and the broader galaxy. Leaving becomes imaginable as reaching a region where the sun is no longer the dominant presence. In this period, the difference between a journey to the moon and a journey beyond the solar system becomes clearer. The moon is a few days away in travel time if high speed can be achieved. The planets are months to years away. The outer boundary of the sun's domain, if defined by gravity or distant comets, is thousands of years away at plausible speeds. This contrast begins to sort imagination into different categories. Some journeys feel like near futures, others feel like distant futures. The idea of leaving the solar system may sit in the distant category, but it is no longer an undefined dream. It is a named challenge with a scale. The key contribution of this stage is that it supplies a language of feasibility. A person can now say, in effect, that if a rocket can deliver a certain change in velocity, and if it can carry a payload of a certain mass, then it can reach orbit, escape Earth, and if enough energy is added, escape the sun. This conditional structure marks the transition from imagining to planning. It is still far from building, but it is closer than any earlier era. The next inward step is the moment when leaving Earth becomes real, when rockets reach space and then orbit, and when spacecraft are sent outward beyond the planets. Once this happens, the imagination of leaving the solar system changes again. It no longer depends only on calculations and stories. It becomes anchored in actual trajectories and actual probes. At that point, humans can not only imagine leaving the solar system, but can witness machines doing it, and the idea becomes part of lived history rather than purely a projected future. When rockets finally reach space and then achieve orbit, the imagination of leaving the solar system crosses from theory into lived capability. The change is not only technical, it is psychological and cultural. A boundary that had existed for all known human history, the boundary between the breathable world and the airless above, is crossed by machines and then by people. The sky is no longer only observed, it is entered. From this point forward, imagining leaving the solar system is not an abstract exercise detached from reality. It becomes a question of scaling what is already being done, going faster, lasting longer, navigating farther, and enduring harsher environments. Early spaceflight begins with suborbital rockets that briefly rise above the atmosphere. These flights prove that a vehicle can travel through near vacuum, that guidance and control can work above the air, and that instruments can operate in space. They also reveal new problems: heating during ascent and re-entry vibration acceleration, and the challenges of controlling a vehicle without atmospheric surfaces. Each problem is addressed with engineering solutions. The accumulation of solutions builds confidence that the space environment, though harsh, can be managed by design. This confidence is part of what makes later thoughts of leaving the solar system feel less like fantasy. Orbit is the next threshold. When an object is placed in orbit, it is no longer simply rising and falling. It is moving around Earth at high speed, continuously falling without landing. This demonstrates in the most direct way the earlier insight of universal mechanics. It also opens a new kind of travel once in orbit. A vehicle can change its trajectory, with additional burns leaving Earth on a path around the Sun. Orbit becomes a staging ground. For the first time, leaving Earth is not a one-time leap. It is a sequence of maneuvers within a known physical framework. Soon after orbit is achieved, spacecraft begin to travel beyond Earth. Some are sent to the Moon, some are sent to other planets. Each mission expands the reachable map. The Moon missions demonstrate that navigation through cislunar space is possible, and that a vehicle can cross the space between Earth and the Moon in a matter of days. They also demonstrate that living beings can survive in space for limited periods with life support systems. The Moon becomes not just a visible object, but a visited place, turning older imagination into a measured path with flight times and trajectory corrections. Interplanetary missions follow. These missions demonstrate that spacecraft can leave Earth, enter solar orbit, and travel to other planets over months and years. They show that deep space navigation using radio tracking and celestial reference frames can guide a craft across vast distances. They show that gravity assists can reshape trajectories, letting a craft gain energy and reach targets that would otherwise be unreachable with available propellant. Each successful interplanetary mission adds to the practical vocabulary of leaving. Trajectory design becomes a field. Mission planning becomes a discipline. The solar system becomes a place where routes can be drawn. In this period, the meaning of leaving the solar system begins to shift from pure imagination to a real, if distant, mission goal. At first, missions focus on planets and their moons. The outer solar system is reached by probes that take years to arrive. These probes reveal the complexity of the giant planets and their rings and satellites. Yet they also reveal the vastness beyond. Each time a probe passes an outer planet and continues outward, it carries the possibility of leaving with it. The craft does not stop at Neptune and fall into a void. It continues into a region of long coasting, where the sun grows fainter and the signal to Earth grows weaker. The physical definition of leaving also becomes sharper as space science advances. The solar wind is discovered as a continuous flow of particles from the sun. The heliosphere is recognized as a bubble carved in the surrounding interstellar medium. This provides a measurable boundary, the heliopause, which can be crossed by a spacecraft. Before this understanding, leaving the solar system might be imagined only in gravitational terms or in the sense of passing the farthest planet. With the heliosphere concept, leaving becomes an event that instruments can detect a change in particle populations and magnetic fields. This is a crucial step because it turns leaving into a definable mission objective. As probes travel farther, the idea of an interstellar mission becomes a topic of serious discussion. The first probes that are placed on outward trajectories fast enough to eventually reach the heliosphere boundary are launched not as interstellar craft in a modern sense, but as planetary explorers whose paths naturally continue outward. Their continued outward motion becomes a form of unplanned interstellar approach. Over time, their mission goals extend to include measurements of the outer heliosphere. Humans begin to witness a machine approaching the boundary of the Sun's plasma domain. This is the moment when imagining leaving the solar system becomes entwined with actual telemetry and actual distance. The idea is no longer only a story. It is a line on a tracking chart. This era also reveals the limits. Spacecraft require power often from solar panels near the Sun and from radioisotope sources farther out. Power declines over time. Electronics age. Propellant for attitude control is limited. Communications become harder as distance grows, because signals weaken and delays increase. A probe can coast for decades, but confirming what it encounters requires that it remain alive and able to transmit. The technology of leaving becomes as much about longevity as about speed. The solar system is not hard to leave because a wall blocks the way. It is hard to leave because it is large and because missions must last a long time. Human spaceflight also clarifies the gap between robotic leaving and human leaving. Humans can travel to orbit and to the moon with great effort. Sustaining humans for years in deep space, protecting them from radiation, providing food and water, and managing psychological strain are far harder challenges than sustaining a robotic probe. The age of early spaceflight therefore separates the concept of leaving into two paths: robotic exploration that can extend outward over decades, and human exploration that remains close to Earth for practical reasons. Yet even for robotics, leaving the solar system remains a long project. The first outward probes demonstrate the beginnings, not the completion. The cultural imagination responds to these achievements with new forms of story. Science fiction begins to incorporate real orbital mechanics, real rockets, and real constraints. The idea of leaving the solar system is portrayed with greater realism, including long travel times and the problem of propulsion. The public begins to understand that reaching other planets takes years, not days. This understanding matures the idea of leaving. It makes it less about sudden departure and more about sustained motion through a vast environment. At the same time, scientific discoveries about the galaxy and the universe continue to expand the context. The Sun is recognized as one star among many in the Milky Way. The distances to nearby stars are measured. The scale of interstellar space becomes clear. This creates a second sobering contrast. Leaving the solar system, even in the heliopause sense, is far easier than reaching another star. The heliosphere boundary is a reachable frontier within decades. The nearest stars are far beyond, requiring travel times of many thousands of years at current probe speeds. This contrast helps define what leaving means. It can mean a boundary the Sun itself creates, not a journey to another system. By the late 20th century, the idea of leaving the solar system becomes anchored in the paths of specific probes. The outbound trajectory is not a metaphor. It is a measured motion. The craft's distance is tracked in astronomical units. Its signal travel time is measured in hours. Its power output is monitored as it declines. The mission becomes a slow crossing of the outer layers of the Sun's domain. This is where the age of imagining leaving becomes an age of watching leaving occur. The concept becomes historical. The next inward step is to focus on the moment the idea of leaving the solar system becomes explicit in human planning and language, not just implicit in outward trajectories. This includes the point when scientists and the public begin to speak of interstellar space as a near-term goal for probes, and when the heliopause crossing becomes an anticipated milestone. From that point, the imagination of leaving is no longer only about what could happen someday. It becomes about what is expected to happen in a certain span of years, turning the phrase first imagined into a real moment in modern history. As spaceflight becomes real, the language used to describe motion beyond Earth becomes more precise, and one idea rises to the center of serious discussion: escape. In earlier centuries, escape is a metaphor for ascent or departure. In the age of modern physics and rocketry, escape becomes a measurable condition. A vehicle can either remain bound to a planet by gravity, returning again and again in an orbit, or it can be given enough energy to leave that binding and never return unless acted upon by something else. This concept turns departure into a threshold problem. It also creates a ladder of thresholds. Escaping Earth is one threshold. Escaping the Sun from Earth's vicinity is another. Escaping the solar system in a meaningful physical sense begins to take shape as the highest rung of the ladder that current machines might someday reach. The first rung is the difference between ballistic flight and orbit. A rocket that rises and falls follows a path controlled mainly by gravity after its engines stop, but it remains bound. It returns. Orbit changes the story because the vehicle has enough sideways speed that its fall curves around Earth. The vehicle remains bound, circling Earth repeatedly. In this view, orbit is a kind of controlled falling stable enough to last for months or years if drag is low. The key point for imagination is that orbit is not a boundary in itself. It is a condition of motion that can be changed by adding speed. If an engine burn increases the vehicle's speed, the orbit grows larger. If it increases speed enough, the path becomes an escape trajectory. The transition is continuous in physics, but feels discrete in outcome because the vehicle either returns or it does not. Escape from Earth becomes the first widely discussed threshold because it is tied to the Moon and to interplanetary flight. To send a spacecraft to the Moon, a mission must place it on a trajectory that reaches lunar distance. To send a spacecraft to another planet, the mission must free it from Earth's gravity well so that it becomes primarily a traveler around the Sun. This is the practical meaning of Earth escape in the space age. It is not the end of gravity because the Sun's gravity remains. It is the transfer of dominance from Earth's pull to the Sun's pull. Once a craft escapes Earth, it enters a heliocentric orbit. It becomes an object of the solar system in the same sense as an asteroid, though engineered rather than natural. This creates the second rung escape from the Sun, often called solar escape. A spacecraft leaving Earth can be placed on many heliocentric paths. Some are elliptical and remain bound to the Sun, returning again and again through the inner solar system. Others are unbound, meaning the spacecraft will continue outward, forever slowing as it climbs away, but never turning back. Solar escape is therefore the condition that a spacecraft's trajectory around the Sun is no longer a closed loop. In practical mission terms, achieving solar escape is not always the goal because many planetary missions remain bound while visiting targets. Yet the existence of solar escape as a calculable condition means leaving the solar system is no longer an undefined phrase. It has a physical interpretation. A craft can be sent onto a path that will not return and will travel outward into the surrounding stellar environment. The phrase leaving the solar system begins to gather a clearer meaning when these thresholds are discussed together. Escaping Earth is already part of routine interplanetary mission design. Escaping the Sun is more demanding, but it becomes achievable with high-energy launch trajectories and, importantly, with planetary gravity assists. The public and scientific communities learn that a planet can lend energy to a spacecraft by bending its path in the moving gravitational field. This makes solar escape feel less like a distant dream and more like a logical extension of what planetary missions already do. A probe sent to the outer planets can be arranged after its last encounter to continue outward on an unbound trajectory. In this way, leaving the solar system begins to appear not as a separate type of mission, but as a continuation of a deep space mission. Yet this new clarity also exposes an important distinction. Escaping the Sun gravitationally does not immediately mean entering a new environment. The spacecraft is still inside the Sun's extended influence in other senses. Long after a craft is unbound, it still travels through a region filled with the solar wind, the outward stream of particles from the Sun. It still experiences sunlight, though weakened. It still remains under the Sun's gravity, even if it will never return because gravity extends indefinitely. The word escape in physics does not mean leaving influence entirely. It means having enough energy that the path is open rather than closed. This nuance shapes the imagination of leaving. It makes leaving feel both more concrete and less absolute. As scientific understanding of the solar wind deepens, a different boundary begins to enter the discussion, the boundary of the Sun's plasma bubble, later called the heliosphere. This concept provides another way to define leaving one based on environment rather than orbit shape. In a heliosphere framing, leaving the solar system can mean crossing the heliopause where the solar wind's dominance yields to the interstellar medium. The heliopause is not a gravitational edge. It is an environmental transition. This definition becomes attractive because it is measurable. It can be detected by instruments. It can be reached in a span of decades by fast probes. The ladder of escape thresholds therefore gains a new branch. There is gravitational escape, which can be achieved relatively early in a mission. There is plasma domain escape, which requires long travel time, even after gravitational escape is achieved. This layered picture becomes part of how modern humans imagine leaving. In the culture of the space age, escape velocity becomes a symbol of these thresholds. It captures the idea that there is a speed required to break free from a gravitational bond. It also captures the reality that speed is expensive in rocketry because increasing speed requires carrying propellant, and carrying propellant requires more propellant to lift it. The rocket equation makes the costs visible. A mission that aims to leave the solar system must either accept a small payload, use multiple stages, or rely on gravity assists to add energy without carrying additional fuel. This becomes part of the public narrative as people learn that leaving is not blocked by a ceiling, but by energy requirements and by the long, patient travel time that follows. The idea of escape also changes the way time is imagined. In earlier travel stories, time is often shortened by magical speed. In physics-based space, travel time is often long. A spacecraft can travel outward at tens of kilometers per second, which is fast in human terms, yet slow compared with interplanetary and interstellar distances. Once solar escape is achieved, the craft still requires years to cross the outer planetary region and decades to approach the heliosphere boundary. Escape, therefore, becomes less like a dramatic launch moment and more like a state that the spacecraft enters and then carries quietly for a long time. Leaving the solar system becomes a slow unfolding rather than a single act. This reframing influences imagination in subtle ways. A society that understands escape begins to picture leaving as a continuum of stages. Earth, orbit, Earth, escape, solar, orbit, outer planets, outer heliosphere, and beyond. Each stage has its own hazards and its own timescale. The early stages are intense and fast, involving launches and burns. The later stages are quiet and slow, involving coasting, long communication delays, and declining power. The imagination of leaving, therefore, becomes less about heroism and more about endurance. Machines become central characters in this narrative because machines can coast for decades without fatigue, while human bodies require constant support. The phrase "first imagined leaving the solar system" begins to align with the point when people can describe these stages in technical language and believe that at least some of them are achievable. In this stage, leaving also becomes a question of direction. An escape trajectory from the sun has a direction in the sky. It leaves toward a particular region among the stars. This introduces the idea that leaving is not just leaving, it is leaving toward something. For most missions, that something is not a destination star because the distances are too great. It is a direction chosen by planetary alignments, by mission goals, and by the desire to maximize speed. Still, the very act of assigning a direction gives leaving a geographic feel. Interstellar space is no longer an abstract beyond. It becomes a surrounding environment with different directions, each with its own star fields and its own local conditions. The moment humans can speak this way marks a true change in imagination. Leaving the solar system is no longer only a metaphor for the unknown. It is a physically defined state and a set of measurable transitions. Yet this stage still remains largely about principle and planning, because witnessing leaving requires a spacecraft to travel far enough and last long enough. The earliest missions that will eventually leave are launched for other reasons, then continue outward. Over time, the expectation of leaving becomes explicit. The idea of an interstellar milestone becomes a goal that can be anticipated within a span of decades. That anticipation is a new form of imagination, not timeless dreaming, but a forecast tied to actual machines and actual trajectories. With escape understood as a ladder of thresholds and leaving beginning to be defined in measurable environmental terms, the next inward step is the era when imagination is fed by mass culture and by early science fiction and theory, and then sharpened by the first outward probes. This is where leaving becomes not only something that can be calculated, but something that can be tracked, announced, and folded into shared history, preparing the ground for the later moment when the solar system's boundary is crossed, and the idea of leaving becomes an observed event rather than an anticipated one. With escape understood as a ladder of thresholds, imagination begins to settle into a modern shape where it is fed by both culture and calculation. Popular stories, public lectures, and scientific writings circulate side by side, each reinforcing the idea that space is a real environment governed by rules and reachable by machines. The tone shifts again. Earlier centuries can imagine voyages as marvels or as allegories. Now the imagination becomes infrastructural. It begins to include launch sites, tracking stations, radio signals, and the long patience of interplanetary flight. This is the age when leaving the solar system first becomes a phrase that can sound like a mission outcome rather than a poetic horizon, because the conditions for leaving are now visible in the movement of actual spacecraft. In the public mind, the solar system becomes a place with a map-like identity. Planets are no longer only bright points with names. They are worlds with measured distances, known sizes, known seasons, and in many cases surfaces or atmospheres that can be described. Telescopic observation is joined by spacecraft data. Photographs and radio measurements transform the meaning of what is known. The moon is not only a face in the night sky, it is a landscape. Mars is not only a reddish light, it is a planet with polar caps and dust storms. Jupiter is not only a wandering star, it is a giant with bands, storms, and moons. This accumulation of detail matters for imagining departure, because it turns the solar system into a lived geography of the mind. A place with geography can be left not in a mystical sense, but in the simple sense that one can imagine crossing its outskirts. The same period produces a more sober understanding of time. Interplanetary travel is not quick. It is slow in human terms, and it becomes slower as missions reach farther targets. Public expectations adjust as mission timelines become familiar. A spacecraft launched toward a planet may cruise for months or years before arrival. Once it arrives, the most dramatic moments may last hours, and then the long quiet of cruise returns. This rhythm trains imagination away from sudden leaps and toward endurance. It makes leaving the solar system feel like a gradual process, something that happens over decades as a craft continues outward long after its main planetary work is complete. The cultural side of this shift is visible in the way stories portray space. In earlier fiction, the method of travel can be a single device, and the journey can be treated as a brief passage. In the modern era, even popular stories begin to reflect constraints: airlessness, radiation, fuel limits, navigation, and the loneliness of distance. The idea of leaving the solar system becomes tied to themes of long duration and isolation rather than to quick adventure. Even when stories remain dramatic, they increasingly borrow the language of physics and engineering. They refer to trajectories and speed to gravity and escape to the need for life support. This borrowing matters because it changes what audiences accept as plausible. A story that treats leaving as a simple crossing begins to feel less believable, while a story that treats leaving as a long outward coast feels more aligned with what missions demonstrate. On the scientific side, the heliosphere concept increasingly shapes the definition of leaving. Once the solar wind is recognized as a continuous outflow, and the heliosphere is framed as a bubble around the sun, leaving can be defined by crossing a boundary in plasma conditions, rather than by crossing the orbit of a particular planet. This definition is especially powerful because it provides a measurable milestone that can be reached within the lifetime of a spacecraft. The solar system becomes, in this framing, not only a set of planets, but an environment. It has a weather of particles and fields. It has a boundary with interstellar space. Leaving becomes a change in the dominant medium a spacecraft travels through. This is a different kind of border than an orbit. It is not an abstract line on a map. It is a physical transition that instruments can detect. The first spacecraft that eventually approach this boundary do not begin as interstellar missions in the pure sense. They begin as planetary missions designed to explore worlds in the outer solar system. Yet from the moment they pass their last major planetary encounter, they become something else as well. They become outward travelers on paths that will not return. Their motion becomes a continuing experiment in how far a human-built object can go while still functioning. Each year they travel farther, the idea of leaving shifts from speculation to tracking. The distance is not imagined. It is measured. The signal delay is not guessed. It is recorded. The outward speed is not a hope. It is calculated from radio tracking. This produces a new kind of public awareness. A spacecraft is no longer only an explorer of a planet. It is an emissary that continues outward beyond the planets. The idea that it will someday reach interstellar space becomes part of its identity. The spacecraft becomes a marker of time as much as distance. People can count years to milestones. They can learn that a mission launched decades earlier is still traveling. They can see that the solar system is so large that a machine can spend a human lifetime crossing only part of it. This lived sense of scale is a necessary ingredient for imagining leaving the solar system honestly. It prevents the mind from turning leaving into a sudden event. It keeps leaving in proportion to distance and speed. The outward probes also change the language of what counts as a boundary. Before direct measurements, the edge of the solar system can be debated as an abstract notion. After direct measurements become possible, the edge becomes something that can be observed. A probe can measure solar wind intensity, cosmic ray levels, magnetic field behavior, and particle populations. Over time, a pattern emerges as the probe moves outward. The sun's influence in particles weakens. The interstellar influence strengthens. The probe can cross a threshold where the measurements settle into a new regime. This is not merely a conceptual change. It is a data change. The concept of leaving becomes attached to graphs and instrument readings rather than to philosophical definitions. This is one of the most important shifts in the age of imagination, because it ties the idea of leaving to evidence. At the same time, this evidence-based leaving introduces another subtlety. The boundary is not a clean wall. The heliosphere boundary can be dynamic and structured. It can shift with solar activity. It can ripple and change over time. A spacecraft may see gradual trends, then sharp changes, then periods of uncertainty, then a sustained new state. The public idea of leaving must adjust to this complexity. Leaving becomes a process of interpretation rather than a single moment. It requires careful analysis. It may require waiting for sustained measurements. This creates a different kind of imagination, again one that respects ambiguity without turning it into mystery. The age of imagining leaving becomes an age of interpreting what leaving looks like in data. Another cultural transformation occurs through the knowledge that leaving can happen without a destination in mind. A spacecraft does not need to be aimed at a star to be said to leave the solar system. It can be aimed outward with no expectation of reaching any specific stellar system in any reasonable time. It can simply cross the heliopause and enter interstellar space as a region. This makes leaving more accessible as an idea. Leaving becomes a milestone of environment rather than a journey to another sun. It becomes possible to imagine a mission whose primary goal is to measure the boundary and then continue outward, sampling the interstellar medium near the sun. In this sense, leaving becomes a form of local interstellar science, not a voyage of colonization. Yet this is also the age when the gap between leaving the heliosphere and reaching another star becomes widely understood. The nearest stars are far away compared with the heliopause. A probe can cross into interstellar space in decades, but at similar speeds, it would take thousands of years to reach even the nearest stellar neighbors. This gap shapes imagination by separating two dreams leaving the solar system, which is achievable for robotic probes within human planning horizons, and interstellar travel to another star, which remains far beyond current propulsion and life support. The phrase leaving the solar system begins to carry a modest realism. It is ambitious yet within reach for machines. It does not imply immediate arrival anywhere else. This realism also encourages the idea that the first age of imagining leaving the solar system might not be ancient at all. It might be modern because imagining in a serious sense requires both a coherent definition and a plausible mechanism. Earlier eras can imagine journeys through the heavens, but they do not yet have the concept of the heliosphere, the measured scale of the solar system, or the rocket-based method that could plausibly cross those distances. In modern times, leaving becomes imaginable not only as a story, but as a planned event with a timeline. This is a different kind of imagination. It is imagination constrained by reality and therefore capable of becoming history. The narrative of outward probes reinforces this. The spacecraft becomes a long-lived artifact, carrying instruments, radio power, and sometimes symbolic messages. It travels through the outer darkness as a test of both engineering and patience. Every year it remains functional. The public learns that machines can persist far from Earth. This persistence is part of the first serious imagining of leaving because leaving requires time. A civilization must be willing to build something that will still be meaningful decades later. It must be willing to treat a mission as a long thread rather than as a short event. The outward probes teach that such threads are possible. This section therefore marks a turning. The idea of leaving the solar system becomes explicit in language and in expectation. It is no longer only a theoretical consequence of escape. It is a milestone that can be anticipated, measured, and eventually confirmed. The next inward step is the transition from anticipation to announcement, where a spacecraft reaches a boundary that can credibly be called the edge by a chosen definition, and the idea of leaving becomes a dated event in modern history rather than an open-ended projection. The shift from imagining leaving the solar system to treating it as a dated milestone occurs when an outward-moving spacecraft approaches a boundary that has a clear physical definition, and when the evidence for crossing can be established from measurements. In modern terms, the most widely accepted boundary of this kind is the heliopause, the region where the sun's outward-flowing solar wind yields to the surrounding interstellar medium. This boundary is not an edge in the sense of gravity ending, and it is not an edge in the sense of the last comet being passed. It is an environmental transition that instruments can detect. Once that transition becomes measurable, and a spacecraft is seen to be approaching it on a known timeline, the human imagination changes again. It stops being a general dream of someday and becomes an expectation tied to a specific craft, a specific decade, and a specific set of readings. This stage begins before the crossing itself, when the outer heliosphere becomes a real place in data. As a spacecraft travels outward, it carries instruments that measure charged particles, energetic particles, and magnetic fields. Over years, these measurements show that the solar wind grows thinner. The patterns of turbulence and particle energies evolve. The influence of the sun weakens not in the sense of the sun becoming irrelevant, but in the sense that the local particle environment becomes less dominated by the steady outward stream. At the same time, the influence of the broader galaxy begins to appear more clearly. Galactic cosmic rays, high-energy particles originating outside the solar system, become more intense as the shielding effect of the heliosphere diminishes. This gradual trend makes the boundary feel near long before it is crossed, because it reveals a gradient. The spacecraft is not heading toward a wall. It is heading through a long transition zone where the sun's presence fades in measurable ways. The boundary also becomes imaginable as a shape. The heliosphere is not a perfect sphere. It is shaped by the sun's motion through the interstellar medium and by the pressure and magnetic field structure of the surrounding environment. It has an upwind side that faces the direction of the sun's motion and a downwind side that may stretch farther. This makes the idea of leaving directional. A spacecraft's path through the heliosphere has a chosen direction among the stars, and that direction influences how far the boundary is. This is a new kind of imagination compared with older planetary travel, where the map is mostly a flat plane of orbits. The outer heliosphere is a three-dimensional frontier. Leaving becomes something that happens in a particular direction, at a particular distance, after a long cruise in a particular band of plasma conditions. As scientific understanding of the heliosphere grows, the community's definition of leaving becomes clearer and more communicable. Leaving the solar system becomes shorthand for crossing the heliopause into interstellar space, meaning interstellar in the local plasma sense. This shorthand is powerful because it attaches a vast and historically loaded phrase to a concrete set of observations. It also means that leaving is no longer entirely a philosophical debate over where the solar system ends. It becomes a question of whether certain measured properties have changed in a sustained way, consistent with crossing from solar-dominated plasma to interstellar-dominated plasma. The argument becomes empirical. The phrase first imagined leaving the solar system in this modern context begins to align with the period when people can imagine such measurements, imagine such a crossing, and imagine a spacecraft surviving long enough to make the measurement. When an outbound spacecraft reaches the heliopause region, the event is still quiet. There is no visible line. The crossing is registered by the behavior of particles and fields. A decrease in solar wind particles is one key indicator, because beyond the heliopause, the solar wind no longer fills the space in the same way. An increase and stabilization of galactic cosmic ray intensity is another, because the heliosphere's modulation weakens outside. Magnetic field measurements add context, though their interpretation can be complex, because magnetic fields can drape and connect in ways that do not produce a simple discontinuity. The point is that leaving becomes a conclusion drawn from multiple lines of evidence rather than a single reading. This changes how the event is narrated. It is not like a ship crossing a shoreline where everyone sees the land behind them. It is like a ship crossing from one ocean current to another, recognized through water temperature, salinity, and flow, rather than through a visible border. This evidentiary nature creates an important delay between the physical crossing and the human recognition of the crossing. A spacecraft may cross the heliopause on a specific day, but confirming the crossing requires sustained measurements that show the new regime is not a temporary fluctuation. Then those measurements must be transmitted back to Earth over weak signals and long communication delays. Then they must be analyzed. The public announcement of leaving can therefore occur after the physical moment. The milestone becomes a process, not a single instant. This is part of what makes the modern age of imagining leaving distinctive. The imagination includes not only the journey, but the verification. It includes the idea that leaving is something that must be demonstrated with evidence, and that evidence takes time to accumulate and interpret. The first confirmations of such a crossing transform the phrase leaving the solar system into a historical statement. From that point onward, humans can say that at least one human-made object is traveling in interstellar space, meaning outside the heliopause. They can attach a calendar date to it. They can compare it to the launch date and see that the journey took decades. This is a quiet but important change in collective imagination. It teaches that leaving is possible for machines within a long but comprehensible span. It also teaches that leaving does not require exotic physics. It requires patience, careful trajectory, design, durable power, and durable communications. The boundary is reachable, but it is not quickly reachable. This modern milestone also clarifies what leaving does not mean. Crossing the heliopause does not mean leaving the sun's gravity. The spacecraft remains gravitationally connected to the sun, in the sense that the sun still exerts an attraction. The craft's path is still a heliocentric trajectory, even if it is unbound. It also does not mean reaching another star. The distances to other stars remain so vast that at the speeds of current probes, the travel time would be measured in many thousands of years. The milestone, therefore, teaches a precise lesson about scale. There is a reachable boundary that marks the end of the sun's local plasma environment. Beyond it lies interstellar space in the local sense, yet the greater galaxy remains far beyond any practical reach. Leaving the solar system becomes, in the modern sense, an act of stepping outside the sun's protective bubble rather than an act of arriving anywhere else. This precision influences how humans imagine the first moment of imagining leaving. It suggests that earlier eras, which could picture voyages to the moon or to planets, as fantasy, did not yet have the conceptual target that modern leaving implies. Without the heliosphere concept, leaving the solar system could only mean leaving the farthest planet or leaving the sun's gravity, both of which are less anchored to a measurable transition. The modern definition gives leaving a boundary that is both physical and reachable by robotic probes. It makes leaving a mission category rather than an unbounded dream. In that sense, the age when humans first imagined leaving the solar system in a serious, testable way is closely tied to the era when the heliosphere is understood and when outward probes exist to approach it. The cultural impact of a confirmed crossing is also subtle but lasting. It creates a new horizon for engineering building spacecraft designed specifically to reach and study interstellar space near the Sun. It also creates a new horizon for public understanding that deep time in mission terms is possible. A mission can last longer than a person's career. It can be sustained through generations of engineers and scientists. The outward probe becomes a symbol not of speed, but of continuity. Leaving becomes a shared long-duration project rather than a single heroic launch. This is an important shift from earlier travel imagination, which often depends on the drama of departure and arrival. The modern leaving is a long middle A coasting through the outer darkness with a boundary crossing that is known only through data. The boundary crossing also reframes older definitions. If leaving is defined by passing beyond the Kuiper belt, then leaving can occur earlier than the heliopause. If leaving is defined by gravitational escape from the Sun, then leaving can occur earlier still, perhaps even within the inner solar system, depending on launch energy. Yet these definitions lack the same environmental clarity. They are real, but they do not carry the same observational weight. The heliopause definition becomes central because it produces an empirical moment that can be declared with confidence. It becomes the point where leaving becomes history. This section holds the transition from expectation to confirmation as the core. A boundary is approached, evidence accumulates, and a date enters the record. The next inward step is to look at how this modern milestone feeds back into imagination itself, shaping the way people think about future leaving, about faster probes, about what counts as the solar system's edge, and about the limits that remain for human travel. From there, the narrative can move toward the final stage where leaving the solar system becomes not only a fact about a few probes, but a stable element of human thought grounded in measured history and tempered by the true scale of space. Once leaving the solar system becomes a confirmed milestone for robotic probes, the act of imagining leaving changes for everyone who follows. Imagination no longer begins from a blank sky. It begins from a chart of trajectories from known distances and from the knowledge that a machine can survive for decades and cross a boundary into interstellar space in the local plasma sense. This feedback from fact to imagination is one of the defining features of the modern era. It turns leaving into a realistic planning horizon for certain kinds of missions, and at the same time it clarifies how far human travel remains from such a horizon. It also forces a careful distinction between different meanings of leaving because history demonstrates one definition clearly while leaving other definitions still diffuse and far away. The first change is that leaving becomes measurable in time and distance rather than rhetorical. Before outward probes, the phrase leaving the solar system can be spoken as a dramatic idea without an anchor. After outward probes, it carries a sense of duration. It implies decades of travel for a spacecraft moving at tens of kilometers per second. It implies that the early part of a mission may be energetic and crowded with events, while the later part is long and quiet. It implies that mission teams may change over generations as the spacecraft continues to move. This time-weighted understanding alters how leaving is imagined. It becomes less like a dramatic escape and more like a sustained outward drift that must be supported by long-lived engineering. The second change is that the edge of the solar system becomes plural in public understanding. People learn that a spacecraft can leave Earth, then still be inside the solar system. It can pass the orbit of Neptune, then still be inside the heliosphere. It can cross the heliopause, then still be inside the Sun's gravitational reach. This layered picture makes imagination more precise. The solar system is no longer a simple set of planets with an edge beyond the last one. It becomes a set of nested domains, planetary orbits, small body populations, plasma environment, and gravitational influence. Each domain has its own boundary and its own timescale. The ability to hold these layers is part of the modern imagination of leaving. It prevents confusion and it supports more honest expectations. The third change is that leaving becomes a design target. Once a boundary crossing has been measured, scientists can ask what instruments would be needed to study the interstellar medium more effectively. They can ask what power systems would be needed to operate for decades. They can ask what communication systems would be needed to transmit meaningful data from far beyond the planets. They can propose missions aimed specifically at the heliosphere boundary and beyond. The imagination shifts from wondering whether leaving is possible to asking what can be learned by leaving. This is a different kind of imagination, one that treats leaving as a tool rather than an endpoint. This tool-based imagination also changes the meaning of the word interstellar in everyday speech. Interstellar begins to mean, in practice, the local environment just outside the heliopause, not the space between stars in the full sense. People learn that interstellar space is not a distant realm that requires reaching another star. It begins just beyond the sun's plasma bubble. This redefinition makes interstellar feel closer, and it makes leaving feel more achievable for probes. At the same time, it can create misunderstanding because the word interstellar can sound like travel between stars. The modern imagination must therefore carry a double awareness that crossing into interstellar space is real and measurable, and that reaching another star remains vastly out of reach at current speeds. The confirmed boundary crossing also strengthens the role of the heliosphere in how people imagine the solar system's place in the galaxy. The heliosphere becomes a kind of protective envelope that reduces certain cosmic ray intensities and shapes the particle environment inside. When a spacecraft crosses the heliopause and measures higher cosmic ray levels, it provides a direct illustration of this protective effect. This influences how people think about human travel. Human bodies are vulnerable to radiation. If the heliosphere provides even partial shielding, then leaving it would expose travelers to a harsher environment. This adds another layer of constraint to an already difficult problem. The imagination of human departure beyond the heliosphere becomes more realistic in the sense that it must now include radiation risk, not only propulsion and life support. The result is not discouragement, it is clarity. The same clarity influences propulsion imagination. With real probes as benchmarks, it becomes possible to speak about what would be required to shorten the time to leaving. A probe that reaches the heliopause in decades sets a baseline. A faster probe would require higher initial energy, more effective gravity assists, or advanced propulsion concepts. Each option has trade-offs. Higher energy often means lower payload mass. More complex gravity assist sequences depend on rare alignments and increase mission complexity. Advanced propulsion concepts may require infrastructure not yet built. This grounded comparison is a new way of imagining. It moves away from vague, faster-than-light talk and toward a spectrum of plausible improvements. Leaving becomes a challenge of incremental engineering progress, rather than a leap into unknown physics. The modern imagination also becomes more aware of communication as part of travel. A spacecraft can physically travel outward without communication, but it cannot contribute to knowledge without sending data. The farther it goes, the weaker the signal and the longer the delay. Therefore, leaving becomes a problem of antennas power and network support as much as propulsion. This leads to a more systemic imagination, in which leaving is not done by a single vehicle alone. It is done by a vehicle supported by a network of tracking stations, by long-term funding, and by institutional continuity. In earlier eras, leaving could be imagined as the act of a lone traveler. In modern reality, leaving is an act of a long-lived system. This systemic nature shapes how people imagine meaning in leaving. Within the constraints of this narrative, meaning-making is set aside, yet the structure of the project still changes. Leaving becomes an achievement measured in capability and in continuity. It becomes something a society can do if it maintains attention across decades. This is a different kind of challenge than building a fast vehicle. It is a challenge of sustained stewardship. The outward probes demonstrate that such stewardship is possible. They also demonstrate that it is fragile because it depends on long-term stability and on the management of aging hardware. Another feedback effect is the way leaving shapes the language of scale. Once a boundary is crossed, people are forced to confront the enormous distances involved, even in reaching the boundary. If the heliopause is reached only after decades, then the distance to the nearest stars becomes emotionally legible in a new way. It is no longer just a number. It is a factor of hundreds or thousands, compared with a journey already known to take decades. This makes interstellar travel to another star appear not only difficult, but qualitatively different in timescale. It clarifies that leaving the solar system, even in the heliopause sense, is still within the category of solar system exploration, while reaching another star is a generational or civilization scale endeavor. The modern imagination also becomes more nuanced about what counts as the solar system. Some will continue to prefer the gravitational definition, emphasizing that the sun's influence extends far beyond the heliopause. Others will prefer the heliosphere definition because it marks a measurable environmental transition. Others will prefer the planetary definition because it matches a simpler map of the world. The existence of real boundary measurements does not end these debates, but it anchors one definition in data. This anchoring tends to make the heliosphere definition more prominent in public discourse because it produces a datable event and a crisp narrative a human-made object has left the sun's bubble. In this setting, the question of when humans first imagined leaving the solar system can be answered in a more precise historical way. Humans have imagined traveling beyond Earth in myth and literature for millennia. Humans have imagined traveling to other worlds in more structured ways since early modern times. Humans have imagined leaving the solar system as a coherent, testable concept, most strongly in the era when the solar system is understood as a sun-centered system within an open universe, when rockets are understood as a workable mechanism, and when the heliosphere boundary is defined as a measurable frontier that a spacecraft could reach in decades. This is the age when imagining becomes forecasting, and forecasting becomes history. The next inward step is to settle this into a quiet conclusion. A final passage that traces how the earliest sky as dome becomes the modern sky as space. How the idea of leaving evolves from symbolic ascent to measurable crossing, and how the first serious imagination of leaving belongs not to the oldest myths, but to the modern moment when physics, engineering, and data make the boundary both definable and reachable. The long arc from the earliest sky to the modern idea of leaving the solar system is an arc of change in definitions. At the beginning, the heavens are a ceiling. They are an ordered surface above the human world, useful for timekeeping and navigation, rich in story, and bounded by the limits of breath and muscle. In such a world, leaving is not a concept, because there is no place beyond the sky that can be treated as a distance. There is only above, and above is a boundary. The first changes come not through technology, but through attention. The wanderers are tracked. Their motions are recorded. Patterns are compared across years. The sky becomes predictable. Predictability makes room for models. Models make room for structure. Structure makes room for scale. With scale, Earth begins to be measured. The moon becomes a body at a distance. The sun becomes an object whose position and apparent size can be compared, and whose distance can be attempted. The stars become so far away that their lack of parallax suggests an immense depth. In this stage, the cosmos is still often pictured as layered and enclosed a set of spheres that gives each body a place. This architecture brings order, but it also keeps the heavens as a closed domain. It offers a map without a route. The sun-centered idea breaks the old centrality. When Earth is placed in motion, the planets become part of one system governed by a shared relation to the sun. Retrograde motion becomes a matter of perspective. The solar system begins to appear as a coherent structure, inner worlds moving quickly, outer worlds moving slowly, all circling a central star. At the same time, the enclosing star shell becomes less stable as a concept. The universe begins to open. Stars begin to be treated as distant suns distributed through space. The cosmos becomes less like a room and more like an expanse. Once the cosmos is an expanse, the solar system can be imagined as a region inside it, rather than as the entire structure. The possibility of an outside takes form. Yet imagining an outside is not the same as imagining a journey. The journey requires a bridge between the motions of Earth life and the motions of planets. Universal mechanics provides that bridge by unifying falling and orbiting. An orbit becomes a natural consequence of motion under gravity. Escape becomes a threshold of energy rather than a mythic ascent. A spacecraft in principle becomes imaginable as an object launched with sufficient speed to orbit to escape Earth and to enter a path around the Sun. In this framework, leaving the solar system becomes in principle the same kind of problem, a matter of enough speed to be unbound from the Sun, and a matter of enduring long travel times through a vast domain. As industrial society makes machines common and distance conquerable on Earth, and as rocketry becomes a calculated engineering problem, this principle begins to look less abstract. Rockets are understood as propulsion that works without air. The rocket equation reveals the cost of speed. Multi-stage designs are proposed. The idea of leaving Earth begins to shift from philosophical possibility to conditional feasibility. Even then, leaving the solar system remains far beyond immediate reach, but it becomes a named extrapolation rather than a vague dream. The solar system itself becomes more clearly mapped, and the idea of other star systems becomes plausible, as stars are understood as suns with similar materials. The imagination of leaving gains a wider context. Leaving could, in principle, mean crossing from the Sun's domain into the domain of other stars. Modern spaceflight converts these conditional ideas into demonstrated capability. Orbit is achieved. Earth escape becomes routine for interplanetary missions. Spacecraft travel to other planets and gravity assists show that planetary motion can be used to reshape a path and increase energy. Outward probes continue beyond their last planetary encounters, coasting into the darkness. As solar wind physics matures, the solar system gains an environmental boundary, the heliosphere, and leaving gains a measurable definition. The heliopause becomes a frontier that can be approached and crossed by a spacecraft. This is where the phrase "leaving the solar system" begins to become something more than a story. It becomes a forecast tied to a craft and to a timeline. It becomes a milestone that can be anticipated within decades rather than within indefinite future time. When the first spacecraft cross the heliopause and measurements show a sustained change consistent with interstellar plasma conditions, the idea becomes a dated fact. The crossing is quiet, revealed by particle counts and magnetic fields, rather than by a visible line, and confirmed through careful analysis rather than immediate spectacle. Yet the effect on imagination is large. It proves that leaving under at least one meaningful definition is possible without new physics and without fantasy. It also proves that leaving is slow. It takes decades even for fast probes. It requires that machines endure that power and communication persist, and that a society maintain attention long enough to receive and interpret the data. Leaving becomes a matter of continuity as much as propulsion. This modern turning changes how earlier imaginings are understood. Humans have told stories of ascent and voyages to the sky for thousands of years. Those stories show the mind reaching beyond the local world. Yet the specific idea of leaving the solar system depends on having a solar system concept, on treating the heavens as open space, rather than a ceiling on having physics that defines escape, and on having a realistic mechanism that could operate without air. It also depends on having a boundary that can be described in physical terms. Under this lens, the first serious imagination of leaving the solar system, in the sense of imagining a definable and testable crossing, belongs most strongly to the modern age, the period when heliocentrism, universal mechanics, rocketry, and heliosphere science come together, and when outward probes exist to make the idea more than hypothetical. The age when humans first imagine leaving the solar system is therefore not a single year and not a single person. It is an interval during which imagination becomes increasingly constrained by knowledge and increasingly empowered by capability. It begins when the sky becomes a space of objects rather than a roof of signs. It strengthens when the solar system becomes a coherent system around a star. It becomes serious when escape becomes a calculable threshold and rockets become a plausible mechanism. It becomes historical when the first machines cross a measurable boundary and send evidence back. In that sequence, the first imagination is a gradual turning of thought from an enclosed dome to an open expanse and from symbolic ascent to measurable departure. The final calm picture holds steady after the last section, as the long path of ideas rests in the same simple frame that makes the solar system understandable. A closed sky becomes a structured sky, then a mapped sky, then an open space. The planets shift from omens and wanderers into bodies with paths. Earth shifts from center to participant. Motion shifts from pattern to law. Escape shifts from metaphor to threshold. Travel shifts from story to calculation, then from calculation to telemetry. The phrase leaving the solar system, once it exists at all, becomes meaningful only when the solar system is understood as a local domain around a star, and when the outside is understood as a continuous environment rather than a barrier. In that quiet modern sense, leaving does not look like breaking through a wall. It looks like a gradual thinning of the sun's influence in particles and fields, and then a sustained change in what surrounds the traveler. Even when a crossing is confirmed, the craft continues outward in the same silence, still within the sun's gravity, still moving at the same steady speed, still separated from Earth by hours of radio travel time. The imagination that first forms around such a crossing is not an imagination of arrival. It is an imagination of persistence measurement and scale shaped by the knowledge that space is large enough to require decades for a single boundary, and large enough to make most other boundaries seem distant beyond planning. The age of first imagining leaving when viewed through this lens is an age of turning the sky into space and turning space into something that can be crossed by rules slowly, without drama, and without losing the clarity of what a boundary really is.